class, and welcome to Chapter 6, which is going to be all about exponential functions. We're going to start with Section 6.2, which is explaining what exponential functions is. We're going to include Section 6.1 actually as part of the Chapter 7 material. So we're going to start today with this Section 6.2 video. By the end of today's lesson, you will be able to graph exponential functions, solve exponential functions, and identify exponential functions. An exponential function is the product of an initial amount and a constant ratio that is being raised to a power. So you're going to see this equation right here. Y is equal to a times b to the x power. That a is the initial amount. Notice that the initial amount cannot equal 0. So we have to start with something. And then the b value, this constant ratio, is going to be greater than 0, and it can't be 1. If it was just going to be 1, then it would be just multiplying by 1 over and over, because 1 raised to any power is 1. You're also going to see this written in function notation, so f of x is equal to a times bx. Notice also that this exponent is attached to the b and not to the a. So if it makes you more comfortable to put parentheses around that b value so that you know the exponent is only attached to the b, you can go ahead and do that. And then the other thing that we're going to look at within this unit is called an asymptote. And this is a line that a function approaches but will never touch. So we'll get into what that looks like a little bit more in a moment. We're going to start off by graphing the function. We're going to do this by creating a table. When you are creating your table, you want a couple negative values. We're going to include 0, and then we're going to have a couple positive values. So you would go ahead and do 12, and then in parentheses 1/6, and then we'd start with to the negative second power, and that is going to give me 432, and then to the negative first power is 71, 0 is 12, 1 is 2, and 2 is 1/3 or 0.33 repeating. So that's the table of values that we are going to go ahead and graph. Obviously, this is not going to fit on the graph as we have it scaled. We need to make it all the way up to 432. I'm going to go ahead and count by 50s to get all the way up there. So we've got 50, 100, 150, 200, 250, 300, 350, 400, 450, and 500. So now I'm going to go ahead and put my points on the graph. So we're starting at -2, positive 432. Then we've got -1 at 72. Then we've got 0 at 12. We've got 1 at 2. And we've got 0 at 1/3. Notice when I connect these, we've got a huge drop off between the points. This is why we have an exponential function. It means it starts out slowly and then rapidly increases. This asymptote that I referred to on the first slide is the line that it never touches. So no matter how far we kept this table going, if I put in 3, 4, 5, 6, it would continue to get closer and closer to 0, but we're never going to actually hit that 0 line. So that's what our asymptote would be. So now we're going to answer the rest of the question. We're looking at our domain, which is going to be all real numbers. We can plug in anything we want for x. When we're looking at the range here, we're looking at our y values. All of our answers, all of our green line values are going to be greater than 0. Note, it is not greater than or equal to 0 because we have that asymptote at 0. It's never going to actually hit 0. Then we've got our y-intercept, which is going to be at 0, 12. Notice this A value in your equation, this is A and this is B, this A value is your y-intercept. That is your initial amount that we are going to have within our equation. And then our asymptote is the line y equals 0. That's that line that we're never going to touch. The y values will never actually hit 0, and they're never going to go below 0. Go ahead and try this one on your own. So for our table, we have the values starting at -2, which is 0.44 repeating, then -1 at 1 1/3. Then we've got 0, 4, 112, and 236. Again, we have this asymptote right here where it's never actually going to touch 0. Domain is still all real numbers. Y's are still greater than 0. Our y-intercept this time is at 0, 4. And again, our asymptote is that line of y is equal to 0. Now we're going to go ahead and write out these functions. In order to do that, we're going to need to be able to identify the b value, that constant ratio of change, and our a value, that starting amount. In order to find your b value, you're going to look at your outputs. So I'm going to take 729 and I'm going to divide by 2,187. That's going to give me 0.3 repeating, or 1/3. I'm going to go and double check that, make sure I didn't make any errors by using the second pair. That's also going to give me 0.3 repeating, or 1/3. So that b value, the constant amount that we're changing by, is 1/3. Notice I took the second answer and divided by the first answer. And then I took the third answer and I divided by the second answer. So you're always dividing by the one that's bigger or further down the chart. Our a value is always going to be this starting information. So in this case, our a is 2,187. So then our final equation, we're going to say f of x, so our function is equal to our starting value, 287, times our constant ratio of 1/3 to the x power. When you are typing this in on the online book, you'll use that little exponent. When you're typing it into Edpuzzle, you're going to have 287 parentheses 1/3, and then you're going to use Shift 6 to get that caret, and then you'll put the x there. So that's how you would write it out on Edpuzzle, including that f of x part. Go ahead and try this one on your own. We divide, we find that our constant ratio for this one is going to be 3. Our starting value is 5, so we get f of x is equal to 5 parentheses 3 to the x power. We're going to go ahead and solve a few of these now. So a certain bacteria population doubles every 20 minutes. Beginning with 10 cells in a culture, the population can be represented by the function b is equal to 10 parentheses 2 to the t power, where b is the number of bacteria and t is the time in 20-minute increments. How many will there be after 2 hours? The biggest thing you need to pay attention to with exponential functions is what your variables stand for. So in this case, t stands for 20-minute intervals, and we're looking at 2 hours. So we need to figure out 2 hours is how many 20-minute intervals. So 2 hours is 120 minutes, and we need to split that into 20-minute intervals, so we end up with 6 intervals of time. Then it becomes simple. We're just going to go ahead and plug in, and we're going to say b is equal to 10 times 2 to the 6th power, which results in an answer of b is equal to 640 bacteria in the culture after our 6 intervals of time. Go ahead and try this one on your own. In this case, our t, our time value up there, is the year since 2000. Since it's 2005, it is 5 years after. We plug in that 5 and get 206.50 billion liters of soda. Last thing we're going to talk about is being able to identify exponential functions. The easiest way to look at this is to look at the change in y. So notice with both of these, our x changes are consistent. So that's not really going to help us out that much. What we're looking at is how did I get from 64 to 32? How did I get from 32 to 16? So you can use that same idea of finding that b value like we did when we were writing the equations. So I'm going to check, and I'm going to say 32 divided by 64, which is going to give us 1/2. Then I'm going to double check and say 16 divided by 32, which is again 1/2. So this here is an exponential function because we have that constant ratio of 1/2. If we come over here to the other chart, we're going to start by doing 125 divided by 100, which is going to give me 1.25. Then I'm going to go to the next one, which is 150 divided by 125, which is going to give me 1.2. So notice that ratio doesn't stay constant. So the other thing then we would need to check is to see if it's a linear function. So I'm going to do 125 minus 100, which gives me 25, and then 150 minus 125, which again gives me 25. So this is going to be an example of a linear function because we're changing by an addition or subtraction amount. So if it's an exponential function, you're going to have that constant ratio, which can be found by division. If you have a linear function, you're going to have that constant ratio, which is found by subtraction. Go ahead and try this one on your own. In this case, you have a constant ratio of adding 4 every time, so this is going to be a linear function. If you have questions about this or anything else from the lesson, please let me know when you get to class.